We now look at what we call dimensional analysis. And this is an analysis of equation based on their dimensions, which are mass, length, and time. You could also use the units instead of dimensions, but we use the dimensions here. The units would be kilogram meters per second, and dimensions of mass would be m is a mass dimension, and the length is an L, and the T is a time, so mass, length, and time. Now, dimensional analysis tells us that equations must be dimensionally homogeneous, which means that each term that is added together, like these three terms, is one term, second term, and a third term, they are added together. They must have the same dimensions. So whatever is the dimensions of the first term must be the same as that of the second term. The second term consists of two parts, a v and a t. And here it consists of an a and a t squared. Now, these are two terms which are multiplied together to give us the second term. You can multiply two different dimensions. So the speed is distance over time, and time is times. They can be multiplied. But you cannot add a meter or a distance to anything other than a meter or a distance. And the same over here. So all must have the same dimensions. Secondly, the dimensions on the left-hand side must be the same as on the right-hand side. So these are added together. They have the same dimensions, but they're equal to whatever's on the left side, and the dimensions here must be the same as the dimensions of each of these. So let's see if that holds. We can write the dimensions of x, which is a distance. X is a distance. Let's write them here first. X, f, which means the final position, but that is a distance, and it's a length, and the v is a velocity, which means it's a derived unit, it's a distance over time, and a is an acceleration. We haven't seen the acceleration yet, but it's a derived unit, and it's a distance over t squared. So the units would become meters per second, and meters per second squared. Now, if we look at the dimensions of x, which is a length, we would write L, and this is an L, and speed is a distance over time, and t is time, and we have a 0.5. Now the constants have no effect over here, so we can just leave it. The a is a L over t square. It's L over t square, and this is a time, so it's t and it's squared. And now we can see that the t will cancel here, and we'll be left with a length and a length, and the t square will cancel with the t square and length. So each term has the same dimensions, and the dimension on the left hand side and the right hand side are the same. So this equation is dimensionally homogeneous. It does not mean that the equation is still correct, but if it were not dimensionally homogeneous, it would have meant the equation is not correct. In this case, it tells us that it's homogeneous, it's likely to be correct. Now we need to do some experiments to verify whether it is or not. Now let's see, is this equation dimensionally correct? So v is, see over here, it's a velocity, so it's a distance over time. So we can write it as an L over t, and the acceleration is L over t squared, and the t is t, so we can cancel out one t, and that becomes L over t. All right, so it is dimensionally correct. Now, as another example, is this equation dimensionally correct? So L is a distance, acceleration is a distance over t squared, and t is a time, which is t, and that becomes L over t. Okay, so the left hand side is L, right hand side is L over t. It is not dimensionally correct. So, okay, but we do think that if something is moving in the x direction, then how far would it go should depend on the time, should also depend on the acceleration. So x should depend on a and t. So we can say that x depends on a and t, but we find that a times t is dimensionally not correct. So maybe there's a power over here, and that would make the equation dimensionally correct and maybe also physically correct. So what could be a possible equation? What could be a correct equation for x? And so we just say, okay, it's a to the power, that's the equation at, a to the power n, and m to the power m. Now, what could be possible powers of n and m? So we use dimensional analysis, and we say the dimension on the left hand side is x is a distance, and acceleration is distance over time square. So it's L over t square to the power n, and t is a time to the power n, m. And well, we can write this to the power 1. Now, for an equation to be dimensionally homogeneous, the power of L on the left side must be the same as the power of L on the right side. Similarly, the powers of every other term must be the same. So if I write the powers of L, then the power of L is 1 on the left side. On the right side, L to the power n, and there's no other L. So it's n. And therefore, we have the solution n equals 1. Now we go to the power of t. So on the left hand side, there is no t. So the power of t is 0. Now, why is the power of t 0? Because you could write it as L to the power 1, t to the power 0, which is just L times 1, because t to the power 0 is 1. So you can assume there's a 1 here, make it t to the power 0. So t has power 0 on the left side. On the right side, it's n and a square, and that's in the denominator. So it's minus 2n. Okay, the powers are, power of a power is multiplied, so it's 2n, and that's negative 2, so it becomes minus 2n, and here it becomes m, and the powers are added together. So if you have, for example, x squared times x cubed, it becomes x2 plus 3. Okay, so the powers are added together. So we add the m and the n. Well, not the m, the minus 2n and m. Now, using this result that we already have from the first equation, we can say 0 equals n is 1 minus 2 plus m, which gives us m equals 2. And therefore, that's our second solution, m is 2. And then this equation becomes a to the power n, which is 1, and t to the power 2, or simply a t squared. And that is what we also had here, a t squared. And well, these are all 0. So this is a powerful way in which, if we know what x or anything else would likely depend on, then we can just multiply them together and get the appropriate powers. Then by experiment, we can verify if this is indeed correct or not. In this case, when we do the experiments, what we find is that that's equal to half at squared. So this half is a constant, which we do not get by dimensional analysis. By dimensional analysis, we get the powers of these terms. Now, it's a very powerful tool, especially for chemical engineering and mechanical engineering. That's used quite a lot. And now let's do one more example on this. That is, what's the acceleration of a particle moving in a circular path? So that would give us centripetal acceleration, or we'll go on later on to get the centripetal force. So we know that if something is going in a circular path, going around in a circle, okay, then that's the radius of the circle, and at that point it has a velocity in this direction, so it's going like this, okay. So the acceleration should depend on the velocity and should depend on the distance. So we say the acceleration should depend on the distance and the speed, and it should depend on some power of these. So now by dimensional analysis, we will look at and find the powers R and M. And this is a constant of proportionality, which we will ignore because dimensional analysis does not help us there. Now the dimensions of A, acceleration, is it's meters per second square, so it's L over T square. And the dimensions of R, which is a length, to the power N, and the speed is meters per second, or distance over time, so L over T to the power M. And this, of course, is to the power 1. So now we equate the powers of the different terms, so power of L. So L is to the power 1 on the left hand side. On the right hand side, L is to the power N and M. So we add L and M. So we have one equation. Now we equate the power of T. So it's T squared to the power 1, so it's simply T squared, but that's 1 over T squared, so the power is minus 2. On the right hand side, we don't have any N. We have N in the denominator, so it's minus M. Okay, so we get one answer. M equals 2 from here. We can plug M equals 2 here, and we get 1 equals N plus 2. That's this equation, and therefore N equals 1 minus 2 minus 1. So N is minus 1. And with this, our equation becomes some constant R to the power N, which is minus 1, and V to the power 2, which we write as K V squared over R, which is the correct form of the centripetal acceleration. We call it AC to indicate it's a centripetal, or something going on in a circular path. So that's the equation that we get from here.